I'm glad to represent carbon upcycling today in order to give you an overview about our company, our strategy, and also our goals. So I will skip the disclaimer. As you know, cement industries are responsible of the major, are one of the major industries responsible on CO2 emissions. So the emissions become more and more important, and then they need more solution in order to lower down this CO2 emission. They are responsible of about 8 to 9% of global CO2 emissions. And that's why solution has been emerged in order to lower down this. So carbon upcycling, we're focused on lowering down the CO2 emission by capturing the CO2 from the atmosphere, and then by using different materials to be then used for construction as a low carbon cement. So carbon upcycling has been operating in 2021 with more than 45 employers and has secured with more than 70 million USD dollars. So we're working with different partners. One of them are the most world largest construction material companies like CRH and CEMEX. So we have been founded in 2021. We built the first commercial demonstration, and we aim to scale up our low carbon cement building materials to 120K in 2030. So I will represent to you the strategy of our company. So based at Calgary, we use different solid feedstock like coal ash, steel slag, clays in order to capture the CO2 from different industrial streams and to transform this CO2 into permanent material storage in the material. And then the materials was been then used as a supplementary cementitious material for buildings, construction, and etc. So we produce materials with more than 40% of strength compared to the ordinary Portland cement, and we reduce up to 60% of the CO2 emission compared to the Portland cement industries. So this is our global strategy called MACE process. So it's a mechanical assisted chemical exfoliation, and we use that at Calgary for the moment. And then there is another approach in parallel is to use other feedstock rich in critical minerals and rare earth elements in order to extract these minerals and then reuse the recovered residue as supplementary cementitious material. I will detail this point in the next slides. So in 2021, we built the first commercial demonstration with more than 6,000 TPA. And then in 2023, we built the second one as a commercial demonstration with more than 17,000 TPA. Our materials has been already used and deployed on the roadside walks and also for home foundations. So we built the confidence with our clients in terms of the used materials and also in terms of the process. As you know, the price of the cement in North of America is about $155 per ton. So we aim to lower down this price by using the low cement material. So we aim to achieve $50 to $60 per ton of these materials, and the plant built in Mississauga, which is under construction and should be worked soon. One of our largest world partner is CRH or Grove Ash Grove. So we aim to produce more than 30,000 tons per year of low carbon cement in this project, and by consequence, so we reduce also the CO2 emission. So the economic benefit of this project is to find the new jobs, to maintain also the existing jobs, and also to reduce material delays for developers. So now I present to you also another approach of carbon upcycling technology, which is aimed to extract the critical minerals and the rare earth elements from different feedstock. So as you know, critical minerals become more and more essential for the new technologies, for batteries, energy, communication, and also for the defense. And also, you know that the supply of these elements become more and more limited due to the geopolitical concerns. So carbon upcyclings aim to extract these critical elements from different feedstock locally, and then to limit or reduce the dependence of the chain supply, and also to protect our resources. So we aim to use different feedstock rich in rare earth elements and the critical minerals like coal ash or mine tailings. We apply a process called advanced mineral recovery, which allow us to recover the critical elements in the solution and also allow us to recover the residue to be used then as a supplementary cementitious material. So we have a dual benefits here, the critical elements recovered as a solution and also the residue that aim to be used later as supplementary cementitious material. So our process allows us to recover more than 75% of critical metals, among them vanadium, chromium, nickel, copper, zinc, and etc. So it's allow also to recover more than 50% of the solid residue and then to be used as SCM. So to close the loop, the residue recovered in this process is then used for CO2 capture. So we capture the CO2 from the atmosphere in the form of a stable magnesium carbonate or calcium carbonate. So we're reducing this form to 20% of the cement replacement. We have more than 20% of cement replacement in this case, and we can reduce the global demand of the cement annually in the world. So to give you an overview about our achievements, so we were able to have a permanent storage of carbon dioxide and lowering down the CO2 emission in this case. So we have a cost-effective method to do that by using the MACE treatment. And we also we were able to use materials with a higher strength than the ordinary cement used in the construction and buildings. And also we have been able to replace 30 to 40% of the Portland cement in this case. So thank you for your attention, and we are looking for any development project in the next by attending this event with low carbon cement. Thank you very much.
Hi, thanks for your presentation. Question, I see mechanical treatment, thermal activation, filtration. Do you guys need absolutely renewable energy to make this process less carbon intensive?
Okay, so in this case, we are using different feedstock, which is mainly for this kind of a process. It's different waste materials. So, and we want to selectively extract some critical minerals by keeping the matrix as it. That's why we're applying different steps in order to extract the target metals without dissolving the matrix. So in this case, we have more than one step. We are following thermal step filtration and also some washing steps. In terms of energy, we are now trying to scale up and to have the capex in this for this process and to see if it's how much in terms of energy we need to achieve this goal.
Okay, thank you. Algoma Steel in Sault Ste. Marie. I don't know if you're familiar with them, but Algoma Steel has mountains and mountains of slag. I've asked them the question, what are you going to do with all this slag? And the answer is really, we don't know quite yet what to do with it. So I'm wondering if that may be some input material for you for your process, or maybe look them up. But my question is, what is the energy balance or the CO2 balance based on how much CO2 does it take for you to produce this cementitious product, as opposed to how much you're storing? So is there like a number? Is it?
In my head, there's not a specific number because it depends on the feedstock. It depends on what is the composition of that feedstock. If it's rich in calcium or magnesium in order to form this permanent storage of CO2. So each feedstock has a specific number, but one of the examples is about 800 to 900 kilogram of CO2 per ton of feedstock material.
Can you tell us a little bit more about the advanced minerals recovery aspect of your solution?
For the critical minerals?
Yeah.
At this point, we just have the solution of the mixture of critical minerals. We don't go into the step of separating these elements and recovery them. So we are looking for any partnership here to do the separation and the recovery of this critical. We just have a concentrate of critical elements and rare earth element at this point.
Okay, thank you.
Thank you.
too. So, the application for the cement side, like the materials, have you looked at waste for mines? Because it could be a valuable binder in terms of their mix and what they use within the feedstock backbone.
Yeah, that's a good point. Maybe I will consider later in the, we will consider it in the future. Thank you very much for this remark.